Welcome to our ERSP project, Predicting Future Memory Access, which is our main goal. We are Alianna, Dillon, Himangi, and Samprithi. So to start off, we'd like to briefly introduce a couple of key concepts such as the main problem, possible solutions, and our solution. This way, you could have a better understanding of our research once we explain it. Let's move to the next slide. A key idea to understand is Moore's law. It is a prediction scale by Gordon Moore in 1965 that predicts that the transistor density per silicon integrated circuit doubles every year. In doing so, the overall system performance increases by a consistent percentage each year. Since this is a pretty tall order, microprocessor fabrication has focused on increasing the instruction execution rate of a central processing unit, aka a CPU. The CPU's instruction cycle is to fetch instructions from an instruction memory, decode it, and then execute it. To speed up this process, researchers focused on creating machine learning algorithms to prefetch these instructions from memory by predicting future memory accesses based on existing data. These accesses typically have patterns, and we'll further explain the idea of prefetching.
So, going over the performance of the memory has not increased as drastically as its microprocessor counterparts. In fact, the gap in performance between the microprocessor and the DRAM, which is the dynamic random access memory, is said to be double every 2.1 years. This divergent trend between the microprocessor and the memory leads to a phenomenon called the memory wall or the performance gap. By solely focusing on the increase of performance in the microprocessors, computers have fallen victim to excessive memory calls wait time, essentially hitting a memory wall in performance. As a result of this wall, a large amount of energy and time is wasted in transporting data between the CPU and the memory. With application becoming larger and more complex each year, this necessity for memory access mitigation is becoming more apparent. There's also the issue of the memory bottleneck problem, which is the shortage of memory when the computer system does not have sufficient or fast enough random access memory, which is also called the RAM. It can also occur when there is memory leaks, which is when a program allocates memory incorrectly. This memory bottleneck slows down the transportation between the CPU and the RAM, and memory blocks are typical.
Continuing off, this situation cuts the speed at which the RAM can serve information to the CPU, which overall slows down the system's performance. One way to alleviate the bottleneck is through prefetching. Prefetching is a method of populating cache with predetermined essential data. With a limited cache estate, this approach is not ideal and can cause more harm than benefit if the cache is congested with unnecessary data, causing an even longer runtime waiting for the cache to clear up. With machine learning as an emerging field, pattern recognition is an ideal solution to this problem of memory filtering. By enabling the processor to determine the set of data in the high-speed caches prior to the time of instruction execution, the latency of memory access would be hidden. With machine learning, the system would be able to learn which pieces of essential memory would be necessary to complete a task and eliminate any unnecessary data that would otherwise congest the cache. In this implementation, our scheme intends to refine machine learning prefetching. We understand that this is a lot to take in under a short amount of time, but the gist is that we want to speed up the process of getting information from memory so a computer can run faster. There are limitations to this that arise due to a limited cache capacity, but we can train our machines to fetch these instructions ahead of their execution time. Our solution was to work on how to predict the future memory access by getting the delta between addresses of adjacent accesses. The memory accesses usually have some patterns, and a prefetching mechanism can predict these future access patterns to a memory location. We were first introduced to this idea by our research instructor, Professor Zhu. She explained a simple example of a pattern to start us off. If the processor needs to access data stored in memory location 10,000 at cycle 100 and access the data stored in memory location 11,000 at cycle 200, and then access the data stored in memory location 12,000 at cycle 300, a prefetching mechanism can predict a future access to memory location 12,000 based on the previous accesses and send a request for access to that data at cycle 200, which is before it is actually needed at cycle 300. When it is actually needed, that data would already be available, and this can improve performance. To go about our project, Professor Zhu assigned us to a PhD student mentor who gave us 3 data sets that we had to parse through. Data parsing is a method where strings of data get converted into different types of data. For example, if you have data in the form of raw HTML, a parser will convert it into something more readable and understandable. In our case, we were given thousands of data about memory accesses of a CPU. Despite seeming like a lot, our mentor often reminded us that these are actually only small chunks of information. So going from left to right, we have a timestamp of the access, a system memory controller number, address number, channel, rank, bank, and row numbers. Our mentor liked to explain how information is taken from these is synonymous to roads and parking lots. You can consider channels as highways, ranks as doors, banks as parking lots, and rows as parking spaces. Only one car can fit inside a parking space, right? Therefore, if you're looking for something, you have a lot of cars you have to go through, and you'd have to search the trunk of one, take it out of the parking space, bring another one in, and check the trunk of that. So this is very inefficient, which is why we're supposed to first understand the patterns of these accesses. Then we'd be able to train the machine to find these patterns in a similar way. And data parsing is a huge part of our research, and we spent significant time analyzing what we were given. So we separated our data into something more readable and understandable to us. And the data was separated into files by channel, rank, and channel, bank, and rows. Then we made it more specific by separating by system memory controller numbers, because each system memory controller has its own channel. So in the end, we had several files to try to come up with any patterns.
An average CPU can perform millions of instructions per second. In fact, the frequency for a CPU is typically in the giga order of magnitude, whereas memory is ordinarily in the megahertz order. Therefore, when working with data of this magnitude, it'd be nearly impossible to manually sift through the data to discover patterns that indicate a particular memory access. Therefore, it is necessary to mitigate the number of data entries by differentiating independent data. It is similar to a bag of marbles, let's say. It is difficult to count the number of red marbles if there are multiple colors, so it's easier to sort the marbles and then count. We isolated our data to bank 0 and channel 0, as well as the memory controllers, thereby minimizing the number of data entries. While there is not a particularly correct answer when determining how to parse data, it is a trial and error process that has numerous papers discussing various parsing methods. When determining potential patterns to data, visualization is a useful tool to reveal explicit patterns. As mentioned earlier, the method to parse data is debatable and subjective. With our method, we were able to import our data into a graph to display using Python libraries, such as NumPy and Pandas. By plotting row access over time, we were able to visualize the memory access characteristics and potentially import this data into a machine learning algorithm, which would then be able to predict a row access in the future.
When we were choosing a machine learning algorithm, we needed one that could predict which row will be accessed at a given time in the future. So forecasting is the process of predicting the future using current and previous data. And the major challenge that we faced is understanding the patterns in the sequence of data and then using that pattern to analyze the future. So deep learning has proven to be better in understanding the patterns in both structured and unstructured data. And deep learning has proven to be better in understanding the patterns in both in both types of data, and our task fell into time series forecasting problem category. In the end, we chose LSTM, which is long short-term memory, and LSTM was designed to learn long-term dependencies, and it remembers the information for long periods. LSTM networks are well suited to classifying, processing, and making predictions based on time series data, like what we had, since there can be lags of unknown duration during important events in a time series. LSTMs were developed to deal with the vanishing gradient problem that can be encountered when training traditional RNNs, or recurrent neural network. In conclusion, we learned a lot about data parsing, how machine learning research is conducted, and we basically learned that there are different types of algorithms that already exist, and each one has its own limitations. It's all about trying to figure out through research which one would be better, and also try to come up with something that could be more efficient than others. But overall, we spent way too much time trying to analyze the data that we were given. And at this moment, we haven't really been able to test, but testing would be checking the data files we were given and checking if the results of the access patterns that the algorithm comes up with is the same. So in the future, we definitely do less analysis, even though it's a very important part, but we try to do it faster, so therefore we'd be able to actually get into the machine learning part, writing the algorithm and making it better and testing it, and do that process more. And so that concludes our presentation. Thank you very much for listening.